Hey everybody. So we are here. We are doing another live office hour for Organic Chemistry 1 with Chegg. I'm partnering with Chegg to give you Organic Chemistry 1 help all semester long. So once again, we're doing this every Tuesday, uh, 5 p.m. PST, excuse me. And you can go ahead and check out that QR code at the top left and go to Chegg's website. You can see all of the subjects that they are doing these office hours for. So you can get help with all kinds of other subjects. We here are going to be focusing on Organic Chemistry 1. Feel free to ask questions in the chat. I will try to address them. Please keep them Organic Chemistry 1 specific as much as possible. And I have some of my own questions here that I have prepared. So once again, we started out going over nomenclature and conformational analysis and isomerism. Then we hit SN1, SN2, E1, E2. We started doing addition reactions. So we're going to pick it up there. We're going to do a few more addition reactions, and then we're going to get into some other kinds of reactions that are typically taught roughly around addition or right after addition reactions. So yeah, once again, feel free to ask questions that are OChem 1 related, and we're going to do this for an hour and see how far we get. So let's take a look at some of these. So the first question here, draw the product of the following transformation. So we have an addition reaction. Now, with an addition reaction, we know that the pi bond is going to act as the nucleophile, and we have HCl, right? Let's go ahead and draw that covalent bond in there. And what's going to happen? We know that the pi bond will act as a nucleophile, and we'll go ahead and pick up this proton, and then these electrons here will stay with chlorine to generate the chloride ion. And so what will that leave us with? That will leave us with this carbocation here. Now, the thing that we need to be aware of is, just like when we were learning SN1, right? The first step here of SN1 and this addition reaction is going to generate the same intermediate. It's going to generate a carbocation intermediate. So this is just like if there was a bromo group there and that left and left a carbocation intermediate there. If we have a secondary carbocation or a primary, but typically those are not able to form very readily. So if we have a secondary carbocation that is adjacent to a tertiary or a quaternary carbon, we will get either a hydride or a methanide shift respectively. So what we mean by that, in this case, we have a secondary carbocation next to a quaternary carbon. This carbon is attached to 4 other carbons. We will get a methanide shift, which means CH3 minus. That means this one of these methyl groups, or any of the 3 actually, with the electrons in the carbon-carbon bond, right, CH3 minus, will shift to go ahead and neutralize that carbocation, and we will therefore generate the more stable carbocation intermediate. So this is what we will end up with. This shift occurs because it is energetically favorable. We're going from a secondary carbocation to a tertiary carbocation that's more substituted and therefore more stable, because there's more hyperconjugation stabilizing that positive charge. So that is going to be our methanide shift. And now, what did we generate in the first step? We took the proton, and now there's the chloride ion. So chloride is going to be, we have Cl minus, we have a plus charge on the substrate, so we will certainly go minus attacks plus, and we will end up with the alkyl chloride. That has been rearranged. And let's go ahead and draw both of the products, because this is, actually, no, it's not. No, it's not chiral, because there are 2 identical methyl groups here, and there are 2 identical methyl groups there. So we will get one product. So this is an addition reaction, but this is right. This is a hydrohalogenation. It is a Markovnikov hydrohalogenation. Remember, last week we were talking a lot about regio selectivity and regiospecificity, as well as stereoselectivity and stereo. Because this pi bond is going to grab that proton, it could potentially leave the carbocation on either the secondary or primary carbon, but we go exclusively towards the secondary carbocation because it is the more stable possible carbocation intermediate. That is an example of regiospecificity. So we go ahead and get that proton leave the secondary carbocation. Then we happen to have a methanide shift because quaternary carbon. If it was a tertiary carbocation, if it was next to a tertiary carbon, we would get a hydride shift. It would just be H minus that shifts because CH3 minus is bigger, but that also can shift. And so that carbocation rearrangement will occur before the chloride has a chance to attack and give us our alkyl chloride product. So that was that first one. Very simple to get started. Let's see if we have any questions. Excuse me. Jacob asks, is tosyl chloride, pyridine, NABR chem 1? It is OChem 1, not Gen Chem 1. That is tosylation is how you protect an alcohol. So if you have OH, or sorry, not protection, it's actually a leaving group derivative. So tosyl chloride, that will give us O tosyl, and then now that's actually a good leaving group, right? We could have some base go in and grab the proton and kick that off, give us our alkene. So tosylation is a way of turning a hydroxyl group into a good leaving group. That's what tosyl chloride is used for. And that's it. Okay, number 2. So this is another addition reaction, but there's a little bit of a twist here. So draw the product of the following transformation. Let's go ahead. We know this is starting out as a dibromination, right? We have Br2 and a pi bond. So the pi bond can go and attack this bromine, kick that off. Now, I think we talked about this last time. Some students do get confused as to how a non-polar diatomic molecule could act as an electrophile, right? HCl, that makes sense because of the polarity of that bond. but Br2 is totally non-polar because the two atoms are the same element. So they have identical electronegativities. And so in this case, it's simply because of the polarizability of that bromine-bromine bond. Bromine atoms are fairly large. Right? So they have very large, fluffy electron clouds, comparatively speaking, to other elements. And so if a source of electron density approaches that molecule, it can polarize that electron cloud and generate a very significant momentary dipole. So there can be these momentary partial charges that will make it electrophilic in the presence of electron excess. So so that's that. And so the first step of dihalogenation is going to be exactly this. So we have, let's just do it like this. Let's add, I like our dashes and wedges here. So we have the bromonium ion intermediate. Okay. Now, the thing is, if this was not aqueous, we know, right, regular dihalogenation, we know that there's a bromide ion that would go and attack, right? It would attack over here, pop that open. But that's actually not what happens when we have an aqueous solution. There are bromide ions in solution, but anytime you are using a solvent that can participate in the reaction, kinetically speaking, it's going to happen every time because the substrate is surrounded by solvent molecules, as opposed to bromide ions in this case, or whatever other reagent is in solution. If that has to swim really far to find a substrate molecule, whereas it can just react immediately with any solvent molecule that is right around it, it's going to react with the solvent. So in the aqueous situation here, water, so these carbons that are connected to the bromine are electrophilic. They're partial positive, and they're actually more electron deficient than just a regular CBr bond. The reasoning for that is that this bromine atom has a formal positive charge. So the electrons in the carbon-bromine bonds are more polarized than normal, right? That positive charge is attracting the electron density in those bonds towards the bromine atom. So these two carbons here have partial positive charges that are more significant than a regular CBr bond. Now, here's the thing. Because of the nature of the bromonium ion intermediate, these bonds are, it's almost as though one of them is beginning to dissipate a little bit as it is getting pulled towards the bromine. And there's a disparity in the ability of these two carbons to accommodate the growing positive charge due to one of these bonds weakening. So actually, the carbon that is more highly substituted will experience a greater partial charge. It will experience a partial positive charge of a greater magnitude and is therefore more electrophilic than the other carbon. So it's a little bit counterintuitive that this nucleophile would attack the more substituted carbon, but that is actually what's going to happen when you do dihalogenation in water. The water molecule will attack the intermediate at the more substituted carbon if applicable, and it is going to pop that open there, and we'll just take the proton transfer as rendered. But we have boom, boom, boom. We have the bromine that got popped over there, and then we have the new hydroxyl, right? Water went on and then deprotonated. Oh, and we have that other methyl there. So there are two methyls, so there's actually no chiral center. There's just one answer here. So this, again, this is dihalogenation. And so if there was not water, if this was not aqueous, you would have the bromonium ion intermediate, and then the bromide would attack and pop that open, and we'd have the trans product, right? We would have it's an anti-addition, the dihalogenation. This also is an anti-addition, but it is the case that because we're in water, water is going to do the attacking. It is going to attack a little bit counterintuitively the more substituted carbon, because it is actually truly more electrophilic, because the electrons in this bond can more readily dissipate because it can better accommodate the growing partial positive charge. So water attacks, pops that open, deprotonates, and we get our alcohol product. So that is a dihalogenation in aqueous conditions. Let's see if I missed anything. All right. Swiggy asks what time. Oh, Chegg already answered. Yeah, 5 p.m. PST every Tuesday. We are doing Organic Chemistry 1 office hours. So basically a nice little tutoring session. You can feel free to ask questions. Okay, let's go and check out the next one here. So we have these 4 transformations. So when we're with Organic Chemistry 1, the most common types of problems are either here's what you start with and the reaction conditions, what do you get? Or here's the reaction conditions and what you got, what did you start with? Or here's what you start with and what you get, what are the reaction conditions, right? How do we achieve this transformation? Those are the 3, probably the most common types of questions that you're going to get. So here's an example where we have the starting material and the products, and we want to figure out what are the reagents that would achieve this. And so here we have, these are all, well, mostly addition reactions. And so we have a pi bond here, and this is clearly a hydration, right? We have added H and OH. The H is implied, so we don't see it. But this carbon has 2 hydrogens on it, and then this is a methyl, so there are 3 hydrogens on there, and then the hydroxyl. So we added OH and H, 1 to each carbon participating in the pi bond. That is a hydration. Now, what is the regiochemistry and stereochemistry, if there is any to speak of? In this case, stereochemistry, we're not worried about that. There is a chiral center, but it is not shown, right? It's not specified what the stereochemistry is, so we're not worried about that. But the regiochemistry is relevant, right? We have a secondary carbon and a primary carbon that are participating in the pi bond, and the hydroxyl went to the secondary one. The hydroxyl went to the more substituted carbon participating in the pi bond. That means this was a Markovnikov addition reaction. This was a Markovnikov hydration. Because again, the hydroxyl went to the more substituted of the two carbons. So what are the conditions for Markovnikov hydration? Quite simple, right? It's just H plus H2O. All we're going to do is oh wait, sorry, in this case no, we need yeah, this is going to be yeah, sorry, we want to avoid that rearrangement. So it's the demercuration, the what is it, yeah, hydration, the demercuration. So that actually, what is the yeah, oxymercuration, demercuration, that is going to be, right, that is what it is. So we need Hg, whoops, HgOAC2 and water, and then 2 NaBH4 and some base. So the reason we need to do oxymercuration demercuration rather than acid catalyzed hydration is because if we did acid catalyzed hydration, there would be carbocation rearrangement. So oxymercuration demercuration is a technique that we can use when we want to do Markovnikov hydration, but we don't want carbocation intermediates, right? Because a carbocation intermediate can rearrange. So if we want to avoid any potential rearrangement, we're going to do oxymercuration demercuration. And that will ensure that we get the hydroxyl on the more substituted carbon without any rearrangement. We will not get the positive charge here, hydride shift. Then we would have ended up with the tertiary alcohol instead of the secondary. So oxymercuration demercuration right there. How about this one? Now we have a pi bond, and clearly this is a hydrohalogenation. We've added hydrogen to one carbon and bromine to the other. And what is the regiochemistry here? The regiochemistry here is anti-Markovnikov. We have a tertiary carbon and a primary carbon, and the bromine ends up on the primary carbon. It ends up on the less substituted carbon. So this is an anti-Markovnikov hydrohalogenation. So what are the conditions for that? Well, we need our HBr, and we need to do this in the presence of peroxides. So it could be hydrogen peroxide, could be some other kind of peroxide. But this is the reagent that is going to very classically promote the anti-Markovnikov regiochemistry by a radical reaction. We don't need to do the mechanism right now. We can just understand that the presence of the peroxides will push this anti-Markovnikov. So this is an anti-Markovnikov hydrohalogenation. Okay, then we have this one here. This is clearly, and you know what? Let's go ahead and write all of these. This is Markovnikov hydration. This is anti-Markovnikov hydrohalogenation. Now, what do we have here? This is syn dihydroxylation. It is a syn dihydroxy. It is a dihydroxylation because we have added two hydroxyl groups, and it is a syn dihydroxylation because we have added them to the same side of the double bond. Right? They're both. We have two wedges, and not a dash and a wedge. If it was a dash and a wedge, that would have been anti-dihydroxylation, And so they would be trans on the product as opposed to cis as they are. And that would require a different set of reagents, right? Even just different stereochemistry will require a different set of reagents. So what is the classic reagent that promotes syn 1,2 dihydroxylation? That is osmium tetroxide. And the reason that osmium tetroxide promotes that is that you have a central osmium atom with 4 oxygens. And so the substrate interacts with osmium tetroxide. Both of those oxygens are connected to the same central osmium atom. So they're being added. It's kind of like heterogeneous catalysis with the hydrogenation, where the hydrogen atoms are coming from the same solid catalytic surface. So here they're just coming from the same covalent molecule. Both oxygens are being added on the same side. So that is syn dihydroxylation. Okay, now last one here, we have cyclopentene, and this is an epoxide. So this is an epoxidation. And so what is the classic reagent for this? That is MCPBA, metachloroperoxybenzoic acid. That is able to insert an oxygen atom into that pi bond and generate an epoxide. So that's really the classic. There's other ways to generate epoxides, but this is kind of the classic go-to. It can be the only one that you memorize. You have a pi bond, it becomes an epoxide. MCPBA, that's the one that you want to use. Okay, so let's see. What did I miss? Okay. Hermes asked, how is it anti-addition? Let's see. That was a few minutes ago. Which one would that be? So I don't think we had an anti one. Oh, maybe you were talking about the this number 2 here. If you're talking about number 2, it is anti because the bromonium ion intermediate, you've got those wedge bonds facing one way, and then whatever's attacking is attacking via SN2, and SN2 operates by a backside attack, right? So whatever direction the bromine is pointing, the nucleophile that's coming in, whether it's the bromide or water, is going to do a backside attack, right? It has to attack from 180 degrees from that carbon bromine bond. That's how it's going to access the LUMO. And that's how the new bond is generated, by dumping electron density into that LUMO so that this carbon bromine bond dissipates and the leaving group leaves, remains tethered to the molecule because it's a 3-membered ring. But that is anti-addition because of the stereospecificity of the SN2 reaction. That's why. Mo for life, can you explain Markovnikov like I'm a 5-year-old, please? Basic terminology at best. So absolutely. All that we're saying here with this regiochemistry is if we have an alkene, right, and we're adding let's say HBr, right? If we get this, right, we have a secondary carbon and a primary carbon, right? This is a secondary carbon because it's connected to 2 other carbons. This is a primary carbon because it's connected to 1 other carbon. So the secondary carbon is more substituted. The primary carbon is less substituted. When you have the incoming group, in this case, the bromo group, going to the more substituted carbon that was participating in the pi bond, that is Markovnikov regiochemistry, right? That is, in this case, regiospecificity for the Markovnikov addition product, right? If you had HBr and peroxides, that would give you the anti-Markovnikov product because the bromine has gone to the less substituted carbon. So these are 2 different structurally isomeric products. The bromine on the center carbon versus the bromine on the edge carbon, they're 2 different products. They're structural isomers. They're not stereoisomers. They're structural isomers. They differ in their connectivity. And so when you get one over the other, that is about regiochemistry, right? Where does the bromine go? So as simple as can be, Markovnikov is when the incoming group goes to the more substituted carbon, and anti-Markovnikov is when it goes to the less substituted carbon. I hope that is clear. It can't get any clearer than that. Diana Hill asks, why is hydrogen peroxide sold in a dark bottle? So the thing about hydrogen peroxide and in general all peroxides is that this oxygen oxygen bond is very weak, and it tends to undergo homolysis. So and it can do so with ultraviolet light. So if this oxygen oxygen covalent bond is struck by a photon of UV light of sufficient energy, you will get two hydroxyl radicals. So homolysis, you see these single-headed arrows. They designate the motion or the activity of single electrons, as opposed to these other arrows. Regular electron pushing arrows tell you what two electrons are doing. It's a pair of electrons, right? It's the two electrons in a covalent bond. It's the two electrons in a lone pair. These single-headed arrows are used in radical reactions because they denote what one electron is going to do. And when you have oxygen oxygen covalent bonds, it's a very weak bond. And it is so weak, in fact, that ultraviolet light, there are other such bonds that homolyze simply due to heat. So the molecule will split in half and you get hydroxyl radicals. So the reason that it's sold in a dark bottle is so that light can't do that and ruin all the peroxide in the bottle. Otherwise, it would degrade very rapidly. Let's see. That's it. Okay. Number 4, draw the product of the following transformation. So we have an alkyne, and then what are these conditions here? We have excess sodium and liquid ammonia. So this is a flashcard reaction, right? We're going to want to just memorize these conditions and know that this is how we go from the alkyne to the alkene. So we have let's see, we're going to go boom boom, and then we're going there, and then come on, 1 2 3, and then another 1 2 1 2 3, and this is going to give us the alkene. 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9. So this would be the way that we go from so when you have an alkyne, right, alkenes and alkynes can be hydrogenated, and if you use simply hydrogenation over platinum metal with excess hydrogen, you're going to lose all the pi bonds, right? You'll lose all the carbon carbon pi bonds. If we did hydrogenation over platinum metal on this, we would just get the alkane. But what if we want the alkene because we're going to do an addition reaction, right? We're going to do a dibromination. We're going to do hydrohalogenation. We're going to do hydration, whatever it is. We want that one pi bond in there. And so this is a way to selectively reduce to the alkene and give the stereochemistry there. If we wanted the Z, we could use Lindlar's catalyst. Lindlar's catalyst would give us the Z. So we have to memorize those three things, right? If you use hydrogenation over platinum metal on an alkyne, you're going to go all the way to the alkane. But then we have sodium metal will give us the alkene, the E, and then Lindlar's catalyst will give us also the alkene, but Z. So we need to know all three of those because we may want to do one of those things at any given time, right? We may want the E versus the Z because we're going for a very particular stereochemistry on the addition product. So we may want one of the alkenes specifically over the other. So that is what that does. We do want to memorize that. Hermes is asking for OChem 1 practice problems. If you go to my organic chemistry practice problems playlist, I've got a ton of those for you there. Sodium makes the transalkene. Yes, that is correct. Okay, Lucy asks, can you explain electrophile and nucleophile? So electrophile is simply a source of electron excess, and an electrophile is a source of electron deficiency, right? Electrophiles love electrons. That's from Greek. And so, for example, yeah, so here we have a nucleophile, a chloride nucleophile, and an electrophile, right? This is the nucleophile. This is the electrophile. So nucleophiles have lone pairs, negative charges, right? And then electrophiles have formal positive charges or partial positive charges. This is the story of organic chemistry, right? Nearly every single reaction is some electron excess meets some electron deficiency, and then they interact, right? We have minusness meets plusness. That's really all it is. Okay. Lucy asks, when do I use RS or ZE? So these are totally different things. R and S. So R and S, like this is an R stereocenter. So R and S are used for chiral centers where you have a carbon atom with 4 different groups attached to it. That's where you use R and S. E and Z describe alkenes. They describe the geometry around a double bond. So here, this one is E because the more significant groups are on opposite sides of the double bond. If they were on the same side, that would be Z for Z same side. That's how you remember that. So that's absolute configuration of alkenes. That's how we describe the geometry around the double bond. Hermes also asks if I will be doing OChem 2 in the future. Maybe next semester. We'll see. Lucy asks, the water is nucleophile, but his H3O plus formation is electrophile. So the proton would be the electrophile in that situation. So water would be grabbing the proton to generate hydronium. That's just an acid-base reaction. So that would just be how we describe that. Okay, let's check this one out. So we want to convert trans 2-butene to cis 2-butene in 3 steps. So here we have, let's first show what we're trying to do. So here's trans 2-butene, also known as E2-butene, and we want to get to cis 2-butene or Z2-butene. So just to be clear, this is E and this is Z. We can say cis and trans in this case because all we have is one methyl on each carbon. So even though cis and trans is relative terminology, that is sufficient to describe these molecules in this case. If we had other groups on those carbons, then we would need to say E and Z because then it's relative, right? Cis to what and trans to what? That's the case here. So this looks a little weird, right? How are we gonna rearrange the geometry of this? Well, we can do some addition reactions, right? We can do addition reactions and then see where we can go from there. So what if we did a dibromination? What would we get there? We would get the dibromination. Let me draw it a little better because there's not enough room. Here is our dibromination product. Now, what can we do here? We just talked about a way to selectively reduce alkynes, right? If we can get an alkyne, if we can get to butane, then it would be up to us if we were reducing to the E or to the Z alkene. So, so what if we try to get an alkyne? And actually, that's why the dibromination was a good idea, right? Let's say we do NaNH2. So NaNH2, that means we've got the minus charge there. Now let's draw in these implied hydrogens. What we can do some elimination. Let's say we get that proton that's going to come down here and kick off that bromine. And so that will give us uh, that will give us this. And then we can actually do that again. And we're just going to count this as one step, right? Because this is all going to go one pot, right? If you put two equivalents of this reagent in there, it's going to go. So they're not really different steps. They're just showing mechanistic steps. But so let's go ahead and get that proton, do that elimination. So it's a double elimination that is going to yield 2-butyne. Right. Now that we have 2-butyne, if we want to reduce to the alkene, we can choose. Do we want E or do we want Z? Because we have sets of reaction conditions that will promote either of those transformations. In this case, we're trying to go to the Z. So we're going to use Lindlar's catalyst. Okay. So this is a great problem because on the surface, it looks like, well, what are we going to do? We need a strategy. All I'm seeing is that we changed the stereochemistry of the alkene. Where's the new functionality? What are the reactions that we're doing? So you really have to think. And what this forces us to do is say, well, I have a pi, but the only thing I have to work with is a pi bond. What can I do with pi bonds? I can do addition reactions. Well, okay, what kind should I do? A hydration? Should I do a hydrohalogenation? Should I do dihalogenation? As it turns out, dihalogenation is a good idea because that introduces 2 halogens with which to do 2 successive elimination reactions to get the alkyne. And from the alkyne, now we have options. So that's going to be it. This, don't stress too much if this doesn't seem intuitive and if it didn't come to you right away as I was explaining it. This is something that you might need to sit and stare at for a little while and go through the possible pathways. What are the addition reactions I know? And is that going to get me to an intermediate that's along a pathway to the target? So these are thinkers. This would be kind of towards the end of an exam, right? You might you see a question like this where you have to think critically here. So that's a good one. Let's see if I missed anything. Yeah, looks like Valentine got it. Well, not H2, but rather Lindlar's catalyst. Can you tell me what a Grignard reagent is? Asked Zaitzi. And so I did include some Grignards at the end of this one. If we don't get to them today, we will start with that next week. Grignard is an extremely important reaction for building larger carbon skeletons. So it's invaluable in organic synthesis and is typically learned sometimes immediately after addition reactions, but if not immediately, then quite soon after. It's a everyone in OChem 1 is going to learn Grignards. So yeah. So we will get to Grignard's pot. Actually, we only have 22 minutes left, so we might not get there today, but we will start with that next week, I promise. Okay, so we've covered a lot of addition reactions. I want to start getting into some other reactions. Like I said, Grignard soon, but ozonolysis is a very important one. So ozonolysis of the following alkene with reductive workup. So let me get rid of some of this. Yeah, we don't need that anymore. So we have reductive workup. We have ozonolysis. What are we going to get? So what does ozonolysis do? Ozonolysis cleaves alkenes. So here we have a double bond. Ozonolysis is going to break that double bond and pull these fragments apart. And the carbons that were participating in the pi bond are now carbonyl carbons. Right now, the workup is important because what type of carbonyl is it going to be? Is it going to be an aldehyde? Is it going to be a ketone? Is it going to be a carboxylic acid? Oxidative workup yields carboxylic acids, but reductive workup is going to yield, in this case, aldehydes, or it could be ketones. If it's a ketone, it doesn't matter either way what the workup is. But when you have a terminal carbonyl, you're deciding whether it's an aldehyde or carboxylic acid. So we are going to get, we have 1, 2, 3, 4, 5. So this carbon right here is the one that was participating in the pi bond. So that is the one that is going to be the carbonyl carbon. And in this case, because we have reductive workup, that's going to be an aldehyde. Right? We're not going to get the carboxylic acid. And so we have that, and we have two of them because this is a symmetrical molecule. So if this was not symmetrical, we would have two products. But in this case, when we pull that apart, we have identical fragments. So we're going to get two of that aldehyde. And so that's what ozonolysis does. So ozonolysis is very easy to recognize because you see ozone in the reagents. Ozone is O3. It's an allotrope of oxygen that is triatomic. And so when you see ozone, you know you're doing ozonolysis. And when you know you're doing ozonolysis, you know that you're taking carbon-carbon pi bonds and cleaving them and pulling the fragments apart. And if you have a linear alkene, you'll get two fragments. If you have a cyclic alkene, it'll pull it apart into a linear product. So that's ozonolysis. So let's do one more because what ended up happening with this one is we had a linear one, so we got two fragments. But as we just said, what about this here? So identify the series of reagents that will achieve the following transformation. We have cyclopentene, and then we have a 1, 2, 3, 4, 5 carbon diester. So these are esters. So what are we going to do here? We know that ozonolysis, we were just talking about it. And as we just said, if you have a cyclic alkene, ozonolysis will cleave that pi bond and turn it into a linear molecule. And so that's what we want. We have a linear product, but we have ester groups here. So how are we going to do that? So let's say let's do the ozonolysis first, right? First, let's do the ozonolysis and see what we get. And so we're going to cleave that pi bond. And why don't we go ahead and do it with oxidative workup? Because we have oxygen content there. It's not a carboxylic acid, but maybe if we get carboxyl groups, we can figure out a way to esterify them. So let's just go ahead and do the version of the workup that yields the most oxygen content possible, because we want more oxygen. We don't want aldehydes. We want more oxygen content. So let's do this with peroxides. That will be a way to promote oxidative workup. And so that is going to give us, we have a 5 carbon, it's going to give us a 5 carbon molecule. And then these are going to be carboxyls, right? So there is one carboxyl, there is another carboxyl. And so now we're just one step away. What can we do here? We can do Fischer esterification. So why don't we do methanol in aqueous acidic aqueous conditions? And so that will protonate the carbonyls, and then the alcohols can attack. And so this is a Fischer esterification. We're going from carboxyl to esters. And so that will be the second step there. So this is the kind of thing that looks mystifying if you don't know about ozonolysis. But if you know about ozonolysis, it's very clear what to do. We're going to cleave that pi bond, pull the molecule apart into a linear molecule. And the question here is, what kind of workup are we doing? Is it reductive workup or is it oxidative workup? And we're just looking at the product and seeing, well, none of this looks exactly like an ozonolysis product, but we want to maximize the oxygen content. So let's go ahead and do oxidative workup. Once you've done that, you have the dicarboxylic acid. How are we going to go to the ester? Well, let's just do Fischer esterification. That's fine. So that's a quick two-step right there. Let's see if I missed one. Electron asks, what's a retrosynthesis? So a retrosynthesis is like, well, I don't have one here, but if we had some target molecule, right? Let's say, how are we going to make this molecule, right? We have some target and you're given starting materials. And then this is called a retrosynthetic arrow. When you see the fat arrow with the two lines like that, that means back in time. And so with retrosynthesis, what we're saying is you have a product, you need a synthetic strategy. Sometimes they give you rules for the starting material that you're allowed to begin with. It'll say you can start with any molecules of 4 carbons or less, or any alcohols or alkyl halides or whatever it is. They'll give you rules about what you can start with, and you got to get to the target molecule. And this retrosynthetic analysis is a strategy for coming up with the synthetic pathway, whereby you start with the target and then selectively modify the target based on transformations you can do, right? So maybe like before this was a alcohol, right? Maybe before this was an alcohol because we know of a transformation in the forward direction. We know that we can oxidize a primary alcohol to get a carboxylic acid. So this would be a retrosynthetic step because we're going back in time. We're saying what could have come before this. And what could have come before this is this thing. And then we do that so that we can go and then this, and before that, this, and before that, this, depending on how complicated the molecule is, right? Very, very complicated organic molecules may require 20 to 30 steps retrosynthetically to get to something that you can go and pull off the shelf and use as a very common reagent to get the synthesis going. So that's what retrosynthesis is. Valentine asks, could you use Baeyer-Villiger oxidation? In this case, no. Oh, and you meant actually for this. So that's interesting. So the thing about Baeyer-Villiger oxidation is that it inserts an oxygen on the more substituted side. So actually that would just end up cleaving some of these carbon-carbon bonds that we don't want to break. So good question though, good thinking, right? You're thinking about inserting, but the other thing though is that would Baeyer-Villiger oxidation could insert that oxygen if we had a ketone, right? If we didn't have a ketone, it's not going to work because it's going to insert it in carbon-carbon bonds adjacent to the carbonyl. So good, interesting thinking. In this case, it's not going to be viable. Okay, let's go to the next one. Yeah, let's see. We have time for, maybe we'll do that first. We'll probably get to that first Grignard one if we can move through these three here. So that at least we'll get our feet wet with the Grignard. So number 8, identify the series of reagents that will achieve the following transformation. So what do we have here? Have we changed the number of carbon atoms? We have not. We have a phenyl ring and then 1, 2, 3 carbons. Phenyl ring, 1, 2, 3 carbons. So we've just changed the functionality, right? All we've done is that we went from an ester to the alkyl bromide, right? So do we have a transformation that will go from an ester directly to an alkyl bromide? No, we do not. We don't have anything that can do that. And so what is something that we can go to as an intermediate? Well, we want to get rid of there's no oxygen atoms in the product. So we want to get rid of the oxygen atoms, which means we're going to do some kind of reduction. So what reducing agent are we going to use based on what is the reduction that we're trying to achieve? And therefore, what is the reducing reagent that we are going to utilize? So given that we are trying to all of this oxygen content, first of all, like, for example, sodium borohydride will not reduce esters. So that's out of the question. There are others that will reduce esters that can selectively go to aldehyde or primary alcohol. In this case, why don't we go ahead and go all the way to the primary alcohol? We're trying to get rid of some oxygen atoms and a pi bond here. So let's reduce it as much as possible. Let's just go ahead and reduce it as much as possible. So let's use a lithium aluminum hydride. That will let us go all the way to the primary alcohol. And so here we are with the primary alcohol. So we have our 3 carbons and then the OH. And so this is good because now we're just going from the hydroxyl to the bromine. So do we have a reagent that can achieve that? How are we going to go from hydroxyl to bromine? So we do have that. And so this is just one that you either know or you don't. Right? We just kind of have to memorize it. But PBr3, right, potassium tribromide, is kind of your classic reagent to go from alcohol to alkyl bromide. And so these are ones that we want to memorize, right? We want to memorize hydroxyl, PBr3, come on, stop it. PBr3 will go to alkyl bromide. Right, we have others, SOCl2, right? There are these reagents that we just kind of memorize that achieve these very common transformations, right? Why do we want to go from hydroxyl to a bromo group? Maybe we want to do an elimination and we don't want to use acid catalysis and have to deal with carbocation intermediates and things like that, right? There's different reasons that we would want to have a bromo group on there instead of a hydroxyl for the next synthetic step, whatever it is. So we went from, we started with the ester, lithium aluminum hydride, reduced that to the primary alcohol. PBr3 will convert the hydroxyl to the bromo group. It will do so. In this case, it doesn't matter because there's no chiral center, but that will be an inversion of stereochemistry. So that operates by an SN2 reaction. What ends up happening is the oxygen atom interacts with the phosphorus atom, and then that kicks off a bromine. The bromine goes around and does an SN2, kicks off the oxygen connected to the phosphorus complex. So that is SN2. And so we want to be aware of the stereochemistry there. That is a backside attack that will invert the stereochemistry at whatever carbon you were doing this chemistry on. So let's see if I missed anything. Gabriel C asks, does a bromide salt not work there for an SN2 type reaction on that hydroxyl carbon? No. So we cannot do SN2 on a hydroxyl group, unfortunately, right? That is a hydroxyl group is not a good leaving group, right? So that is not a good, a carbon that bears a hydroxyl is not a good electrophile for an SN2 reaction. Now you can still do substitution, but you'd have to use aqueous acid. You'd have to protonate the hydroxyl, have that leave, right? That would be that would be more of an SN1, not an SN2. And that opens up a situation where you can have carbocation rearrangement, things like that. So, so no, carbons that bear hydroxyls are not good SN2 substrates. No, this is OChem 1. Definitely. There are certain topics towards the end of OChem 1 that some courses fit into OChem 1, some courses kind of shove into OChem 2. It depends on your institution, but every OChem 1 course is going to go over very basic oxidizing and reducing agents, some of these transformations. This is definitely OChem 1. Okay. So let's go on to number 9 here. So here's another ozonolysis. So O3 tips us off that this is going to be ozonolysis, and this is reductive workup. The dimethyl sulfide is a classic reagent for reductive workup. And so what is ozonolysis going to do? It's going to cleave that pi bond. Now, let's number our carbons, and this has nothing to do with IUPAC nomenclature, but let's go 1, 2, this is just our own bookkeeping. 1, 2, 3, 4, 5, 6, 7. And now let's go ahead and open that up. So we're going to have a 7-carbon linear molecule. So let's go 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And this is, so what do we have? So on carbon 3, remember that when we do ozonolysis, the carbons that were participating in the pi bond are now carbonyl carbons. They're part of carbonyls now. And then the question is, are they aldehydes, ketones, carboxylic acids? Depends on the substitution. If you have a secondary carbon, it's going to be a ketone pretty much no matter what the workup method, right? Because we're probably not going to be breaking carbon-carbon bonds. So carbon 3 was participating in the pi bond, so that is now a carbonyl carbon. So 1, 2, 3, secondary carbon, so that is going to be a ketone. We're going to have a carbonyl there. 4, 5, 6, 7. The other carbon that was participating in the pi bond is carbon 7. So remember, 1, 2, 3, 4, 5, 6, 7. So this is a terminal carbon. So let's go ahead and draw the carbonyl. Now, what is on the other side of this? It depends on the type of workup that we did. Here, dimethyl sulfide, once again, is a classic reagent promoting reductive workup. So we are going to get the aldehyde. If we were using peroxides, if we were using some reagent that promotes oxidative workup, this would be the carboxylic acid. So we would put an OH there. So that is ozonolysis with reductive workup. We had a cyclic substrate, so we have a linear product, a singular linear product, and so that's the product there. So yeah, and once again, it's this is very useful if you get confused with unwrapping a cyclic molecule into a linear form. Just go ahead and number the carbons, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It's just a good bookkeeping method. You don't want to gain or lose any carbon, right? With most of these reactions, we're not gaining or losing any carbon content. So we want to make sure that we have all those carbons conserved. 7 carbons, 7 carbons. The functional groups have changed, but the carbon backbone is not going to change. So number it, number what you get, just to be perfectly clear, perfectly safe, right? No teacher is going to get mad at you for numbering your carbons. Just go ahead and do that. And then it's very easy. 1, 2, 3. 3 is now a carbonyl. 4, 5, 6, 7. 7 is now carbonyl. And then we decided there was hydrogen there because of reductive workup. So that's one more ozonolysis for you there. Okay. So let's just wrap this up really quick. Maybe let's do 2 of them, and then we'll save the other 2 maybe for next time. So draw the products of the following Grignard reactions. So these are very straightforward Grignard reactions. So what we need to understand about Grignard reagents. So here is right when we prepare the Grignard reagent, this is all we do, right? We have we put in elemental magnesium, and usually diethyl ether would be a good solvent for this. And the magnesium ends up inserting itself into the carbon-bromine bond. It's kind of like oxidative addition if you learn inorganic chemistry later. And so what this does is it's an example actually of Umpelung chemistry. So what that means is that it reverses the polarity of the typical polarity of a bond. So usually we have when you have a carbon halogen bond, it is polarized in the direction of the halogen, right? The carbon is partial plus and the halogen is partial minus, and that's why these are good SN2 substrates, because we can have a nucleophile attack the partially positive carbon, kick off the leaving group, and then that's your SN2 reaction. What this does, by virtue of magnesium inserting itself into that bond, we're reversing the polarity of the bond. Because magnesium is actually less electronegative than carbon. And so now, because carbon is bound to magnesium, the carbon is partial minus. So Grignard reagents are a source of nucleophilic carbon. And so if it's nucleophilic carbon, right, this carbon right here is going to do the attacking. It's going to attack the carbonyl, right? Carbonyl carbons, we already know that those are good electrophiles. So that's going to kick that up there. And we are going to end up with an alcohol. So we have our after the protonation, right? This is the aqueous workup step there. And then here is our 3-carbon. We had a 3-carbon Grignard reagent attack right there. And there is our alcohol product. So Grignards generate alcohols. That's what Grignard reactions do. And this is after the workup. So we have the oxyanion, which is protonated in the workup step. So just getting our feet wet with the Grignard. Again, we're going to start with this next week. We're just out of time here. Let me just see if I missed anything. Lesson notes, Danny. No, we don't need to do hydrolysis. You can directly reduce esters with lithium aluminum hydride. Yeah, that's it. So that's it for this week. Once again, I'm here with Chegg every Tuesday, 5 p.m. PST. We are doing Organic Chemistry 1 office hours. I'm progressing through what I perceive to be a typical Organic Chemistry 1 semester of trying to, everybody's at slightly different pace, different timings with their semester, but I'm doing my best to kind of go roughly where you probably are in your semester every given week. And so we'll pick it up with the Grignard reagents, the Grignard reactions next week. Go ahead and check out the code up there for Chegg to see what other office hours they are offering, so you can get all of your study time for math and all your other subjects. But otherwise, I will see you here 5 p.m. PST next Tuesday, and we'll go over some more organic chemistry.